Today's daily equal problem of the day is count square submatrices with all ones, number 1277. For this problem, we're given an m by n matrix of ones and zeros, and our goal is to return how many square submatrices have all ones. So we can take a look here at example one first. Basically, we're given a matrix of, it's a 2D matrix of zeros and ones, and we want to count how many squares of just ones there are. Now we can see in this problem, squares of side 1 are valid, so that would just be like this. We're also looking at squares with 2 sides and squares with 3 sides. So there's a total of 15 squares in this problem, meaning we're going to count each one individually, each one of these individually, each 2 by 2 individually, and then each 3 by 3 individually as well, which would just be this whole chunk right here. So to solve this problem, I drew up this like kind of dynamic programming solution that we're going to walk through right now. So here is our example matrix. This is the matrix we are given. Now to solve this, we're going to initialize our dynamic programming matrix over here. So this is our dynamic programming matrix, and this is our input matrix here. I'll just like that. So as you can notice, this matrix ends at 3. Our dynamic programming matrix ends at 4. And I initiated these side variables to all equal 0. The reason for that is for each value we're going to look at, so we'll call this I of j. Typical like for loop, you have for each integer I in a row, for each integer j in a column. We are going to, sorry, let me put that back. For each I of j, we are going to consider this as the bottom right corner. So how exactly are we going to do this? First things first is we're going to try to identify, is it a 0 or a 1? So if it's a 0, we're going to skip it. We're not even going to bother. Then we can move on. Let's move here. So I would move down here, right? This is I of j. And we're going to check, okay, so does I of j equal 1? It does. Now we're going to treat this as a bottom right corner. The reason I filled this in with 0 is because this is a 0. But we're going to treat this like a bottom right corner. And so for I of j over here, we're going to look at our dynamic programming matrix as I plus 1 of j plus 1. So over here, we're looking at 1, 0. Over here, we're going to look at 2, 1. So I is going to be here, j is going to be here. And basically, we're looking at this index. So we're going to say, okay, this value is a 1, so we know we need to add 1 at least to our dynamic programming array. But the first thing we're going to do is we're going to consider, can this section become a square? Now we know because this is on the leftmost side of our array, it can't, and these two are zeros at all times, but that's basically how we're going to be treating it. So we're going to check the values of these 3 values, and we're going to use that to update this value. So I'll kind of walk through each solution here so you guys can get like a general understanding. I'll point out which node we're looking at so I don't have to keep updating the I and the j. So here we go. We're looking at this one here. We're going to say, okay, this is 0, this is 0, this is 0, but this is a 1, so we'll update it as a 1. Now we're looking at this 0 down here. Okay, this is a 1, but these 2 are zeros. We can't make a square here, and it's a 0, so we'll update it to 0. All right, now we're looking at another 1 here. We're going to look at the up, diagonal left, and left. Okay, these are all zeros, but we know this is a 1, so we'll update it as a 1. Now we're moving on to this one. Okay, so we have a 1, so we know it has to be at least 1. We look up, 1, diagonal left, that's a 0. Left 1. Okay, so this has got to be a 1 because there is a 0 in what would be its square. Now we move on to this bottom one. Again, 1, 1, but this is a 0, so it's going to stay as a 1. Again here, 1, because these 2 are zeros. But now we have this one, which can form a valid square here. So now that we could see that visually, how are we going to code that? So we know for sure it has to be 1, so we're going to plus 1 to whatever our equation is for sure. But what we can do is check the minimum of the surrounding options that would form a square. For example, we're going to look above. Okay, that's a 1. Diagonal left. Okay, that's a 1. And left. Okay, that's a 1. So our minimum value is 1. And then we're going to add it to our 1. So that's going to give us 2. So what we're saying is in this square, we're able to form 2 squares, which is true because we could do 1 here and we could do 1 here. So those are the 2 squares. Now we're going to move on here. Same thing, minimum value around it is 1. So we're going to go ahead and update that to be 2 as well. Looking up here, again, we can't form a square if this is the bottom right corner. So this is going to stay as a 1. And then boom, this one, this slot here, the minimum value around it is a 1. So this can be a 2. And now we're looking at the bottom right corner. The minimum value around it is 2. We're going to add 1. So it becomes 3. And then if we add all of these up, we get the answer is 15, which is our solution. So 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's how we're going to solve this problem. We're going to dynamically go through each position in our regular array one by one, check, is it a 1? If it's a 1, we're going to check above and to the left and diagonal up to the left and see what the minimum value around it is. That's why we have the extra positions here so we don't go out of bounds looking up and left, because technically this is our matrix here. And we're going to look up, left, and left, and we're going to see, okay, what is the maximum amount of squares we can make from this position, treating it as a bottom right square. So a good way to visualize that is this, this equal to this. So yeah, that's how we're going to solve it. So let's go ahead and jump into the solution here. First thing we're going to do is initialize 2 variables. We're going to have an integer called row, which is going to be our matrix.length. And then we're also going to have a column, which is going to be our matrix of 0.length. Those are simply just going to help us kind of shorten up our for loops. And then we're going to have an integer called dynamic programming, which is going to be a matrix. And that is a new integer double array. But remember, we need row plus 1 and column plus 1 because we need that extra room so we don't go out of bounds. Then we're also going to have an integer answer, which will be 0. Now, for each integer, I is equal to 0, as long as I is less than our rows, and I can increase. Same thing for j, so for each integer j is equal to 0, as long as j is less than our columns, j can increase. Now our first rule of thumb is the value we're looking at has to be equal to 1. So if matrix of I of j is equal to 1, then we know for sure we need to at least have 1 square there. So we'll check. What is our dynamic programming of I plus 1 of j plus 1. And remember, the reason we're doing I plus 1 and j plus 1 is because we have extra rows above and to the left. So we're going to treat this like a bottom right corner. So that is going to be equal to the math.minimum of, and then we're going to need 2 math.minimums here. So math.minimum of, first one is going to handle the value to the left and the value above. So we're going to say dp of I of j plus 1, and then dp of I plus 1 of j. So that's our first dynamic programming, or our first value we're comparing to. And then the second value we're comparing to is the dp of I of j. So basically, we're going to treat this like the bottom right corner, and we're going to check above to the left, and to the left, and see what the minimum value is in our dynamic programming array. If it's a 0, we cannot make a bigger square. If it's 1, we can make 2 squares. If it's 2, we can make 3 squares. Whatever the minimum value is, that's what we'll check, and we'll update accordingly by simply adding 1, because we found a new 1 to add as a square. And then we can update our answer as well to plus equal the dp of I plus 1 of j plus 1. That way we can just update it all within the same loop. And then simply return our answer. If we run this, passes our test cases, and if we submit it, passes all solutions. So thank you, and follow for more daily LeetCode solutions.